simultaneously. So section 9.2. We need to talk about light and what light is, because that's going to help us to understand electrons. Some of the stuff that we have learned about atoms came about by studying how light interacts with atoms. So we need to understand what light is. Light is a form of electromagnetic radiation. It's a form of energy. It travels through space at a constant speed. We call that speed the speed of light. And that's 3 times 10 to the 8th meters per second, which probably doesn't mean a lot to you, but that's 186,000 miles per second. Okay, that's crazy fast, right? That's why in the cartoons, I don't know if you ever watched any of those really old cartoons. I remember one. It's fun to watch these and pick apart the physics, because they just violate physics right and left. So the guy blows out the candle on his bedstand, and then he jumps into bed before the room gets dark. Not possible. Not possible. So light always travels at the same speed. And a really interesting thing about light is it has properties of both waves and particles. And understanding light as a wave is not too hard, but when you think about light as a particle, that gets kind of a little crazy to think about. So sometimes it helps to think about something that we can actually see the wave nature of. So here's an illustration of water droplets falling into a pool of water. And what happens as the water droplets fall? It makes ripples. Okay? These are waves. And those waves travel outward, and they can be disrupted by something. If there was a post here, that would cause the waves to move around it. But there's energy in that wave. A wave carries energy. So here is, I guess you could say this is a graph of a wave. It looks a lot, it's basically a sine wave. And so this is what light does. And there are characteristics of the wave itself. Now the speed of all light is the same, 3 times 10 to the 8th meters per second. But these other parameters can vary. The wavelength is the length of the wave. And that could be measured from crest to crest or from trough to trough. And we give that the Greek symbol lambda, which is a lot like an upside down lowercase y. So we'll be using lambda. And the waves travel in this direction. And so you can kind of imagine waves on a lake, and they move, right? The wave moves, but you see the water going up and down. So wavelength is one parameter. The wavelength of the light affects the color that we perceive. So when we see white light, which is like produced by the sun or by an incandescent light bulb, it has all the spectrum. It has the complete spectrum. It has all the wavelengths of light. It's got red light and yellow light and blue light and green light and all those colors in it. When white light passes through a prism, it separates the light into different wavelengths, because the prism bends the light, and it bends differently depending on the wavelength of the light. And so it separates that white light into many colors, and that's where we get a rainbow. When we see a rainbow in the sky, it's the white light from the sun passing through the raindrops, which act as a prism and separate the light, and then we see this beautiful rainbow. We have a cut glass light fixture in our entryway, and when the sun is setting and it comes through and it hits that just right, there's little tiny rainbows all over the room, which the kids think is like magic or something, right? But it's just the light hitting the glass in just the right way and separating into wavelengths. Red light has the longest wavelength at 750 nanometers. Remember, nano means 10 to the minus 9. So the wavelength of light is very, very short. Red light is the longest, and violet is the shortest at 400. And then the other colors are in between. because the light from the sun and the light from light bulbs has all the colors in it, then we see things in color. And what we're seeing is the reflected light. Here's an illustration of a prism. Here's a light bulb going through a slit, just to focus it, passing through a prism, and it separates. It always separates in the same order of colors. And so, when a child draws a rainbow, they sometimes just put the colors in random order. You may look at that and you're like, I know you're trying to draw a rainbow, but there's something wrong about that. And you may not recognize, oh, the colors are in the wrong order. They're always in the same order. It's Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. So indigo is this color, I guess, in between blue and violet. But it always passes in the same order because those are the different wavelengths. Red is the longest wavelength, and violet is the shortest wavelength. And the other colors fall in between. So here's an illustration of a woman getting wet in the surf. She's getting her clothes wet. She has a red shirt. Why does this shirt look red to us? Because the shirt reflects the red light and it absorbs all the other colors. When something looks black, it's because it's absorbing almost all of the light. Something that is white is reflecting all of the colors. So what we're seeing as color is the light that is reflected by that object. It's absorbing the other colors. So that's wavelength. Another characteristic of light waves is frequency. Frequency is given the symbol nu, which is looks a lot like a V, except the second part of it is got a little curve in it. So frequency is nu, not to be confused with velocity, which is V. I didn't make these things up. The frequency is the number of cycles or crests that pass a stationary point in 1 second. And the wavelength and the frequency are inversely related because the speed of light is always the same. Is there no picture? There's no picture. Okay, we'll make a picture. We need a picture. We'll go with black. So that's my bad attempt at a wave. It's a little crooked there. So this distance is the wavelength. And the speed is the speed of light, which we often abbreviate c. I don't know why. 3 times 10 to the... Got ahead of myself. 3 times 10 to the 8th meters per second. So imagine that you are standing over here. I forgot to comb your hair this morning. There you are, standing there, and you're looking at this wave, and you're counting the number of crests that pass. So the wave is moving this way at the speed of light. And so you're standing there, and you're going to count crests of waves for 1 second. Now, obviously, you couldn't do that, but the frequency is the number of these crests that would pass you in 1 second. Okay, so you're standing here, and this is moving, and you're counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, maybe 12 pass. So that frequency is 12 per second. So 1 unit of frequency is per second, or a second to the minus 1. That's also known as hertz. Not Hertz Rental Car Company, but hertz. And you may have heard that in terms of, power or something, it's a 60 hertz or 60 kilohertz, that cycles per second. So if your wave, let's make a different colored wave. Let's go for blue. So hopefully we can see the blue. So if we have another wave that has a shorter wavelength, here's the wavelength for that one, and they're moving at the same speed, which one's going to have a higher frequency? The blue one or the white one? The blue one. They're moving at the same speed, so it's got a shorter wavelength and a higher frequency. So that's what we mean by an inverse proportion. We said they're inversely proportional. So the wavelength is proportional to 1 over the frequency. If the frequency goes up, the wavelength must go down. If the frequency goes down, the wavelength goes up. Okay? Oops. Yes, I don't care that you can't connect to the Evernote server. Stop that. So that's light as a wave, but light can also be viewed as a stream of particles. And this is hard to understand. And so if you don't completely understand it, that is absolutely fine. I don't completely understand it. I don't know that anyone does. And it's okay to not understand something. So we can also view light as a stream of particles, and a particle of light is called a photon. You heard of photons before? Science fiction, Star Wars, Star Trek, fire the photon torpedoes, right? Well, a photon is a particle of light. Sometimes we call it a packet of light. A photon is a piece of light. How can you have a piece of light? Well, it's a really tiny piece. Light carries energy. And the amount of energy carried by that photon is going to depend on the wavelength of the light. If it has shorter wavelength, it's got greater energy. So just down here on the bottom, so here's this wave. And here's a different one. That's really a sloppy wave, sorry. The yellow light has a longer wavelength. The red light there has a shorter wavelength. Which one looks like it has more energy? The one that's going up and down really fast, right? The short wavelength has more energy. It has a higher frequency. Light waves carry more energy if their crests are closer together. So that's how I remember that, is I think of, okay, a wave with a long wavelength looks big and slow, right? And one with a short wavelength looks really kind of hyper, jumping up and down really fast. They're both moving at the same speed, but the one with the long wavelength has less energy than the one with the short wavelength. Okay? It's a little bit like, maybe grandma and the 2-year-old are both traveling at the same speed down the sidewalk, but grandma's just, she's just moving kind of slow. And the 2-year-old is like jumping up and down or going back and forth on the sidewalk, right? Maybe he's not making any forward progress faster than grandma, but he's moving a lot more. He has a lot more energy. So here's a summary slide. You guys can read that.